All right, so for our next talk, Paul will be telling us about the expressive power of some languages for static variability.
Yeah, thank you for the introduction, and I'm happy to see that some people still remain on the sunny afternoon. I want to start with a user story. So meet Alice and Bob. They are C++ developers, and they had a hard day at work, so they're going to a diner to relax a bit. They enter and they're shown this menu where they can create their own sandwiches. So this is like a menu sheet that offers you different ways to configure your sandwich, for example, different kinds of bread or cheeses or sauces. And they wanted to relax, but Bob is eerily reminded of his work. And yeah, Alice has noticed this really resembles variability in their code base. And they're C++ developers, so they're facing C preprocessor annotations all day. So this is an example from the text editors within the code base. So, and you see C++ code annotated with C preprocessor statements. So we are mixing two languages, the normal C code, and in blue, and proceeding with these hashtags, the C preprocessor annotations. And depending on how you define these flags, so how a user configures their code, you end up with different C programs, or C++ programs in this case. So in case of this, and depending on whether Microsoft Windows is the platform, you get different calls for your operating system. So yeah, and now that we think about it, it's not actually just sandwiches or code. There's like many domains, maybe like software, hardware, cyber-physical systems that are subject to variability, where we need tons of ways to configure our systems for the user. Most prominently also the Linux kernel, which is based on C and C preprocessor and offers like over 5,000 configuration options. So there's a huge amount of variability here. So the question is, how can we model and describe variability not just for one of these systems or for one particular programming language, but for all of these kinds of domains? So to give you like an idea of where we want to go with this work, so all of you should probably be familiar with the idea of computation, and we're typically using programming languages to implement computation. So name your favorite programming language, Java, Haskell, you name it. And the semantics, or like the specification of our programs, can be given in terms of Turing machines, the lambda calculus. So this is the kind of formalism we use to say what a program is and what's not a program. So for static variability, we just saw we can use the C preprocessor, we can use aspect-oriented programming like in the previous talk, or sandwich menus. So what's it that we can put in the bottom here? So we want to find like a formal specification for variability across these domains. And there's actually a candidate out there. In the introduction of their own paper, they write, we're like the lambda calculus of variation, and it's called the choice calculus. It's very small. It has just two constructs. The first one is data. So we have some kind of tree, like an abstract syntax tree. And the second one is a choice, which offers us some configuration options. So as an example, let's consider we want to encode a menu for sandwiches, where we have always bread, maybe salad, always cheese, either tofu or meat, and any combination of sauces. So in choice calculus, we could write this down. Oh, where's my cursor? We could write this down in this way. We have at the root of our expression the bread, and the bread has 4 children in this tree. We have a choice between salad or nothing, so we can say we have salad or we don't have salad. We always have cheese, so that's a data child with no children. We have a choice between the patty as being tofu or meat, and we can choose between any combination of sauces. And the semantics then is that we can configure all choices to end up with an expression without choices. So given a configuration, which is a function that tells us for each of these features, salad, patty, sauce, a value which we want to use, we can end up with, for example, this sandwich with salad, cheese, tofu, and ketchup. But it's actually not just choice calculus. There's a whole bunch of formal languages used by different research groups for different analysis, for different problems. And this is just some of the languages I found that have been used in practice. So the question is, how do these languages relate? Do they describe the same thing? Can we transfer research results from one language to the other? If I want to write a new variational analysis or formalize it, prove some properties, which language is the easiest to use for that purpose? So what we do is we want to first see what's the semantics. So what do they describe? Do they describe the same thing? So we want to depict what's the semantics of static software variability. So the idea here is that the semantics of an expression is a function that takes a configuration as input, resolves all variability, and gives us a variant. So in terms of our sandwich example, an expression must encode, like a cookbook, all the information we need to compose our sandwich, the ingredients to do so, and then a user can give us a configuration. The semantics is someone like the cook, who then prepares the final variant, a single sandwich, and a very particular one. So actually, we don't have a semantics of just one language. We want to compare expressions. So we dealt with two of these boxes. We want to have a semantics of two expressions. So how can we compare them? And the basic idea is translation, like building compilers. So the question is, can we translate the expression on the top to the expression on the bottom, and the configurations as well, because these can also be different kinds of data or formats, such that the variants in the end are equal. So can I produce the same variants in both expressions, and vice versa? So based on that, we formulate criterion for expressiveness. So the intuition is that the language can express everything another language can express when we say that this language is at least as expressive, which is a common notion also in the literature. So formally, this means for every expression in the second language, I get an expression in the first language that's semantically equivalent. And we can prove this by building a correct compiler. So if we compile M to L, we show that for every expression, we can find another expression. So given our world of languages used throughout the literature, somehow looks like this. We now want to relate them, draw some arrows into this picture. And the first languages we want to compare for this purpose is the choice calculus. We introduce a new family of language called the n-ary choice calculus, which means every choice has exactly n alternatives. So you can loosely think of this with another intuition for these languages as languages where you have only if expressions. So the choice calculus then on the bottom left is a language where I have any number of elif branches for each choice. N-ary choice calculus has a fixed amount of elif branches, and binary choice calculus on the top center then is a language with only if-else statements. And we then introduce these blue arrows. These are compilers. So these are proofs that a compiler exists from one language to another. And we show that like translating these if and else languages can be done via this language family to an arbitrary degree. We then also relate the binary choice calculus at the top with algebraic decision trees, which is another language which wasn't actually used to model variability until very recently. So this was a language introduced for game theory or some other algorithmic problems. We also compare these languages with option calculus on the top right. So this is a new language we introduced to capture what's the semantics of just if-then statements, because that's frequently used in variational analysis, but never was really formalized. So as you might guess, an if-then statement can always be expressed with if and else, but not the other way around. And finally, there's feature structure trees. I don't have time to talk about these in detail, but this is kind of a modular variability language. We have different modules, and then you can compose them. So not annotating a single tree, but composing the modules. So the part of this relative kind of expressiveness, where we compare the languages by translating, we're also interested in these classical notions of soundness and completeness, and especially completeness is like an absolute measure of expressiveness. Can we express every element of our semantic domain? So formally, we say for every non-empty and finite set of variants, or set of sandwiches, we want to find an expression, we want to be able to build an expression that does exactly that. And in the world of software engineering, this is typically known as differencing, in this case n-way differencing, because we have n trees of input data, want to find the similarities and differences in one expression. Soundness is the converse property as usual, so we want to express only variational trees. So from an expression, we want to be able to find the element in the semantic domain. And we can prove this by showing that all configurations can be enumerated. So we can go to the sandwich dinner, to the restaurant, get all the menus, and just make all the possible configurations on a sheet of paper. So proving soundness and completeness for these languages is actually a bit intricate and complicated, so we use a trick. And you probably know this trick. It's a language called clone and own. It's a common practice in software engineering, unfortunately, where you just duplicate your code to achieve the same result. And this is also a common language used at pizza restaurants. So this is a pizza restaurant from Pasadena. And they just list every single pizza available with lots of duplicate ingredients So onions appears like 10 times on this sheet of paper, and you could also have one variational expression, like the sandwich diner, but pizza places like to do it like this. So, and for this language, just listing all the different variants, it's very easy to prove soundness and completeness, and it's also rather easy to relate to the other languages. So we can then connect some circles, translate clone and own to these other languages if possible, and then can start to derive completeness for free for the other expressions. So the observation here is if one language is complete, and I can translate this to another language, so there's a more expressive language, then this other language must also be complete. So completeness flows along these arrows, and every reachable language will also be complete. So we find that there's this island on the left side, this chunk in the graph, where all languages are complete, the right ones are incomplete. This requires a separate proof, but also is hinted at by us not being able to traverse to the right. And conversely, soundness goes in the opposite direction. So we're lucky, everything is sound, so this means all these languages can be used to describe software variability. So we can conclude here that choice calculus could indeed be seen as a lambda calculus of variation, and so could be algebraic decision trees and clone and own. And we find at least 3 different classes of expressiveness, the complete languages, the incomplete languages, and also the ones on the right cannot be translated into each other. But there's maybe more questions arising here. So if there's multiple complete languages, are these equally good? And if there's different classes of expressiveness, and there's complete languages and incomplete languages, why should I care about incomplete languages? So regarding complete languages, are they equally useful? So let's take this expression from the beginning. If I could translate this to algebraic decision trees or clone and own, I get a combinatorial explosion. That's a well-known problem if you have code duplication and clone and own development. So now we have to list every variant, like in the pizza place. So no, not all languages are equally useful. Sharing of subterms is important. And for the second question, what's the value of incomplete languages? So we know choice calculus is complete. So when looking at our example, everything should be fine. But indeed, in fact, there's this weird empty value. So we can encode like options where we say we can have salad or we don't have salad. We can do this with options, but this requires this empty value, which is context sensitive, depends on our sandwich language or whatever else we're configuring. We can also encode it without these neutral values, but again, this requires duplication, which is annoying. And actually, in the incomplete language of just choices, so just this if-then language, we can avoid these drawbacks because we can encode these optional values, but we cannot express alternatives or other constraints, so that's making this language incomplete. So we conclude that you should probably use both, and that's also what's happened typically in practice, but not in these formal languages. So combining both kinds of expressions is what we recommend. So all of this is formalized in Agda. Every theorem, every definition, every language, every proof. We also provide some tutorials if you want to integrate your own language or translations. And the nice thing is, because this is intuitionistic logic, every proof comes indeed as an executable compiler. So we really have to show that everything works. So you can run the code, translate data sets, for example, and I invite you to have a look at our GitHub repository. So in summary, we witnessed some software developers having troubles with variability in the code. We present a formal framework for comparing the semantics of variability languages. We applied our formal framework to a range of existing formal languages to chart this part of a map of existing languages, and whether they're complete or incomplete. And we implemented everything in Agda. So please have a look, and thank you for your attention.
Any questions to the microphone?
Hello, this was a really cool talk. I was wondering if your framework is able to compare languages that have different kinds of constraints on choices. Like if you had like a sandwich that says like, I can only have cheese if I don't have tofu, or something like you can have new choices if you have one other kind.
Yeah, that's a very good question. So in this realm of software variability, software configuration, that's actually like 2 concerns. One's implementing variability like the languages here do, and then formulating constraints and lots of dependencies. You can integrate this into the languages as well, and there's some like more advanced dialects that do so. So, example, you could, in the C preprocessor, like the practical language, you could like write a huge formula on your macro. If this is selected and this dependency is satisfied, so this would be a naive encoding, and otherwise there's like models for externally encoding any dependencies, checking these, and then using only legal configurations. So in the dyna, this would be like an employee that checks whether the customer filling out the thing would be fine, and only then handing it to the kitchen. Thanks.
Thanks. I really like this talk. So my question is, you have this idea of these complete languages and these incomplete languages, and you say that there are some cases in which the complete ones can express things a little more simply and easily. I guess maybe that's not the best way to start my question. Maybe my question really is, you have a way to translate different variability languages into semantics. Do you have a similar way, or do you think there could be a similar way of translating specifications or like the kinds of variants you would be interested in a particular setting into a semantic objective? Or so you could say maybe this language is complete for this particular kind of variance or this particular set of sandwiches, and whether that would be useful.
Yeah, that's also a good question. So yeah, let me go back to this map. So we have thought of, and I mean also one of the reviewers asked this concern, yeah, you found like one semantic domain, and for this it's complete, but what about these languages on the right? Maybe there's better semantic domains. And there's indeed some syntactic properties, for example, of feature structure trees that make them incomplete, but it's not like that's an unreasonable reason. So that's a choice, a design decision they made for some good purpose. So one could say, let's constrain the semantic domain even more to like account for specific edge cases. And yeah, you could do that. So this is a very loose definition, like the broadest we could think of, that still matches some of the languages out there. Yeah. I hope this answers your question.
Sure, yeah. Thank you.
Thanks.
So you mentioned, we want to be on the complete side, and clone and own is obviously bad, but then you didn't tell us which one is best. Was that on purpose, or is there just no one best?
So the three complete languages we found is choice calculus, algebraic decision trees, and clone and own. But both algebraic decision trees and clone and own have this blow up, so use choice calculus.
Use choice calculus. Yeah. All right. Great conclusion. All right, let's thank Paul one more time.